In this video, we're going to discuss covalent bonds. In our class, we discussed two types of bonding that involve valence electrons, ionic bonds and covalent bonds. I do have a video that's an introduction to both of them where I discuss the differences between the two. And so that might be a good place to start if you feel like you're not ready for this. I also have a set of videos that are specific to ionic bonds. So if you haven't already seen that kind of goes along with this covalent bonds topic. So let's dig into covalent bonds. And on this slide, we're just going to talk about three of the things that we need to consider in covalent bonds. So the first thing is what type of elements will form covalent bonds, and those are the nonmetals. So if I just sketch kind of the outline of a not very neat periodic table, recall that in our periodic table there's a stair-step line somewhere around that spot. And on the left side of the line are the metals. And then on the right side of the line are nonmetals. Including the hydrogen is also a nonmetal. And then along the stair-step line, there's also metalloids, which are kind of in between the two. And for covalent bonds, then what we're talking about are the elements that are in this area, the nonmetals. Now, sometimes metalloids on this side of the line will also participate by bonding with nonmetals in a covalent type bond. So that's one thing. We want to know that covalent bonds are formed when nonmetals bond together. The second thing is the second bullet point, and how these bonds occur is that they share valence electrons, and we'll be talking a lot more about sharing the valence electrons in this discussion. And just as a reminder, valence electrons are in the outermost energy level. So they're the electrons on the very outside of the atom. If you want to review valence electrons, what they are, and just how their relationship with all the other electrons, you can look at review electron configurations, where we'll talk about energy levels and things like that. The third bullet point says that when atoms form covalent bonds, they form a molecule. And a molecule is just a group of atoms that are bonded together. And overall, they do not have a charge. So these are uncharged. And so a lot of times when we're talking about covalent bonds, we might also call them, also known as, aka, molecular compounds. And that name is coming because compounds that have covalent bonds form molecules. So if you see something describing molecular compounds or asking about molecular compounds, then these are compounds that contain covalent bonds because they have little individual units. I think in the introduction to bonding introduction to bonding video, where I discuss ionic and covalent bonds, I have illustrations of the difference between how ionic bonds, their ions get together versus the shared electrons. So that would be another place to review again. Now, this last illustration is not something you have to draw. It is just showing us how we might imagine sharing of electrons. So on this first picture right here, what am I pointing to? This is just showing two separate hydrogen atoms. They, in the Lewis structures down here, which we discussed also in a previous video, they have one dot there. That is, the hydrogen has one valence electrons. And we'll talk more in this chapter about valence electrons as well. And so that would be two of them separate. But if they were to share their pair, notice in the illustration here, now the clouds where the electrons would be are now overlapping and mixing with each other. And when they draw the Lewis structures, they now have two dots in between. That's what we talk about when we say a shared electron pair. Now we're going to, at this moment, we don't have any idea about why they would share or even some of how it's drawn. I just want you to have an image in your mind when we talk about shared electron pairs and what it's meaning to those electron clouds, how they're sharing and overlapping. All right, so you do need to know the three major points on this slide: that covalent bonds are formed between nonmetals, that it occurs with a sharing of the valence electrons, and that atoms that form covalent bonds will form molecules. Now, this is also an illustration. You don't need to be able to draw anything that's on this page. It is just, again, trying to connect those orbitals that we spoke about when we were reviewing electron configurations and connecting that with the idea of sharing. And so for this initial idea of sharing, we're just talking about those orbitals overlapping and mixing with each other. And if you look here, like if we look at this illustration, so here they have 2 chlorine. Chlorine has 7 valence electrons, so it has 7 dots around it. Again, and I know I've already said this, but I'll say it again, I do have a short video on the Lewis structures of atoms. So if you're like, what is that? Go back and take a look at that just to review and make sure you understand. So those 2 chlorine atoms have 7 dots around them. That's the valence electrons. And if they come together to make, this would be Cl2, a chlorine molecule, you'll see that the p orbitals overlap. That's where they're sharing. And in terms of the dots, it's represented by 2 dots in between the 2 chlorine. So you don't have to draw this for me. Again, I'm sharing this slide with you so that you have some ideas in your head when the word sharing is used, how we might illustrate it. Like, what are we talking about? And so I just share this with you so that you can start to form some like I said, illustrations. So things in your head where you might imagine something that we really can't see, but by imagining it, it can help us understand what's going on. All right, so the octet rule was important in ionic bonding, and it is also in covalent bonding. So the octet rule in general says that atoms will gain, lose, or share their valence electrons to have the same electron configuration as the noble gas closest to them on the periodic table. And so a couple things about that. If we're talking about covalent bonding, then we're not going to have the gaining and the losing. We're talking about atoms wanting to share so that they can have the electron configuration of the noble gas closest to them. Now, noble gases, except for helium, have 8 valence electrons. That means they have 2 in their S, whatever level they're on, they have 2 in the S, and then they also, on whatever level they're on, have 2 in the P. 6 in the P. I'm writing the letter N because I don't know if they're in the second level, I think that's neon. I don't have the periodic table right here. The third level, argon. So I don't know which level they're on, but what all noble gases have in common is 2 S electrons in their valence and 6 P. So the noble gases have 8 valence electrons, which is the maximum, and this is very stable. So other atoms in bonding try to also have 8 valence electrons so that they also may be stable. Okay, so that's how, so the covalent rule, the octet rule applies to covalent bonding. Now, a couple main points, I have little arrows. Hydrogen, which only has an s orbital, can only have 2 electrons. So in covalent bonding, hydrogen can have a maximum of 2 electrons around it because it does not have the p orbitals available, so it can't go up to 8. And if you look at the periodic table, helium is the closest noble gas to hydrogen, which also only has an s, so it can only go up to 2. All the other main group elements that we're going to encounter will share to have an octet. Now, I want to mention here, there are some atoms that can have less or more than 8. These are exceptions. For our introductory course, we're going to focus on the main group elements that are going to follow the octet rule. And so if you are going to take the next level chemistry, then when you'll talk about Lewis structures again, and then you're going to be introduced to the atoms that are exceptions to the octet rule, either less, which there's only a few that can have less, and then more. Anything, I think it's after the 3rd period, actually can have more than 8. So let's look at this line right here in the middle, right here, is what I want to look at. And I want to talk a little bit about how it's being drawn and the words that go with it. At this very moment, I just want to focus on how it is drawn. I'm going to teach you how to get to the drawing. Like right now, I'm not going to describe to you why. Okay. So if we look over here on this side, here are 2 separate atoms. There's hydrogen, which has 1 valence electron, and fluorine, which has 7. So if they bond together to make an H and an F, imagine me just sliding these close to each other, and then I would get something that looks like this. So this, oh, it's too big. Let me see if I can make it a little bit smaller. I'd like to highlight but not have it so gigantic. That right there and that electron right there are now between the H and the F, and they are being shared. So this right here is a shared pair of electrons, and we call that a single covalent bond. Okay, it's only one pair being shared, so it's single, and covalent bond means shared. And why it's a bond is it's between 2 different atoms. Now, here's why they like to do it. So now if I look at hydrogen, just looking at hydrogen, do you see hydrogen now has 2 electrons around it? So it went from having 1 to having 2, which is very stable. That's like the noble gas closest to it. And then I look at fluorine, and if I look at fluorine, including the shared pair, it now has 8 electrons around it. So it started with 7, but by sharing, it now has 8. So that when they talk about having 8, like the noble gas closest to them, by sharing, that's what they're talking about. So when they share, now that atom sees 8 electrons around it instead of whatever it started with, the valence electrons. Now this is really over here, let me take over here, right there, And I'm going to erase the yellow so you can see, but right there, that is really how I like to draw things. Get a different color. So that line right there represents a single bond, which is going to equal 2 electrons. So for me, when I start drawing and I teach you how to draw, I'm just going to draw a single line between the atoms, and it's going to represent a pair of electrons. Otherwise, you start getting lots of dots. Now, the other ones around the fluorine are not bonded or shared with anything. Fluorine brings 7 electrons, but only is sharing 1. So it has 3 pairs that are unshared. And we can call them, up here you see lone pairs, or down here, it says unshared electron pairs are called non-bonding pairs or lone pairs. So sometimes the atoms will have electron pairs that I talk about bringing it to the party. I don't know why, I just think about it that way. So they bring electron pairs to the party, but they don't share them with anybody. But they have them because they want to have 8. All right. So on this slide, you do need to know how the octet rule can be applied to covalent bonding. I'm going to repeat this next thing so much, but hydrogen will only have 2 electrons ever, no exceptions. And every other main group element is going to try to have 8 because we will not be dealing with the exceptions. You also need to become familiar with what it means for a shared pair and how we represent them when we're drawing it, and what a non-bonding electron pair and lone pair is representing. Now we're going to practice drawing, and I'm going to teach you how to draw what we call Lewis structures of molecules, and so we'll be practicing and using this some more. So let's think about the periodic table and how it can help us predict the number of bonds and the number of non-bonding or lone pairs that an atom would have when it forms a molecule. So on this slide in red is just a reminder to us that covalent bonds are formed when 2 nonmetals combine, or when you have a metal and a metalloid, and a nonmetal. And so our question is, how many covalent bonds will a particular atom form? Now, for some of these atoms, this will always be true. For other atoms, things like oxygen in particular, nitrogen sometimes, it may vary just ever so slightly. But I have a plan for that, so don't worry. So again, on the bullet points, hydrogen forms only 1 bond. Okay, so this is not an exception. It shares 1 pair of electrons, which means it only forms 1 bond. Then the second thing says atoms with 4, this should be or more, not our more. 4 or more valence electrons form enough bonds to give an octet. And here's the rule that we're going to look at. Now on the next slide, I have a table. I will rewrite that rule on the table. But using the octet rule, we'll predict for everybody but hydrogen that if you take the number 8, because everybody wants 8 electrons, and subtract how many valence electrons the particular atom has, that will give you an idea about how many covalent bonds they'll form. So let's look at the table I have so we have like a reference. So here's just, I like these kind of tables. So I made a table, and I chose from each group a sample element. I just went to period 2. Now notice I don't have groups 1, 2, and 3A. That's because these are metals, and metals don't form covalent bonds, so they're not a part of this discussion. Metals with nonmetals like to form ionic bonds. So we're going to look at hydrogen, which is never an exception, and then we'll look at examples of group 4A, 5A, 6A, and 7A, the nonmetals. I also don't have the noble gases on this table because the noble gases have 8 valence electrons. So with the octet rule, we do not predict that they would form covalent bonds. I will mention that some of the larger noble gases can, with exceptions, form covalent bonds. Again, if you are lucky enough to take our next chemistry class, then you'll be practicing with that more. All right, so let's look at hydrogen first. And this one is never an exception. I'm just going to put a little asterisk here. I don't want to use that color, sorry. I'm going to put an asterisk here and say, I'm just going to say it does not follow the octet rule. 2 max electrons. Okay, and that's a little abbreviated, but that's what we're writing. Okay, so hydrogen is in group 1A. It has 1 valence electron. We predict always that it will only form 1 bond and not have any other electrons around it. This one is not an exception. Okay, so hydrogen will always just form 1 bond. Always, with no other non-bonding electrons, which means hydrogen will never have dots around it that aren't bonded to another atom. So now let's look at the others. So valence electrons, remember a quick way, if all we need to do is figure out valence electrons, is to look at the number in front of the letter A. So this carbon has 4 valence electrons, nitrogen would have 5, oxygen has 6, and the fluorine has 7, which would be true for any of the elements in their group. Now the predicted number of bonds, this is what we had on the last slide. If we're using the octet rule, we say you take the number 8 and subtract the number of valence electrons. And this is true for everybody but the hydrogen. So for carbon, it would be 8 minus 4. So we would predict 4 bonds. For nitrogen, it would be 8 minus 5. So we would predict 3 bonds. Oxygen, 8 minus 6 is 2. And fluorine and the other halogens, 8 minus 7 is 1. So this is how many bonds we would predict. Now, underneath the predicted lone pairs, I want to just draw something that might help some of you. So I'm going to put the letter C for carbon. And remember that each bond I can draw as a line. Now, in this example, and what I'm trying to think about, I'm not really worried what it's bonded to. So it could be a hydrogen, it could be something else. I just want to look at the carbon, and it's bonded to different things. So I also want to remind us that each line that I'm drawing represents 2 electrons that are being shared. Okay, I'm just not saying what it's shared with. All right, so if I look at carbon and I count across, carbon has 2, 4, 6, 8 electrons around it. So it would need no more electrons to have a complete octet. So there would be no lone pairs on carbon. And carbon is really good at following the octet rule. And so we find that carbon does form 4 bonds with no lone pairs. That's very common. Now nitrogen on the next one, we see that it only forms 3 bonds. So it would only have 3 lines. Because it already brings 2 to this party, this bonding party. And so if I were just to have 3 bonds, nitrogen would have 2, 4, 6 electrons. Okay, so 6 electrons is not enough. So nitrogen has, because it brings more electrons than carbon, it has lone pairs on top of it, one lone pair. So then with that lone pair, now if we look at nitrogen, it has 2, 4, 6 that are shared, and then 1 lone pair, and that gives it 8. Right? So we have with it, like, there's 2, 4, 6, 8. So nitrogen with 3 bonds has to have 1 lone pair to have the octet. Now oxygen, you may start seeing the pattern. It would have only 2 bonds based on the octet rule. But 2 bonds is just 4 electrons, right? It would just be 2, 4. So what oxygen has is 2 lone pairs. So it has 1, 2, and then 1, 2. And so it has 2 lone pairs. And then if we look at it, it would have 2, 4, 6, 8 electrons around it. So hydrogen with 2 bonds would have 2 lone pairs. And then fluorine, who only has 1 bond. And remember, the reason fluorine only has 1 bond is because it already has 7 valence electrons. It's the closest to the noble gas, so it has to do the least amount of sharing. So fluorine would have 1 bond and 3 lone pairs. So it would look like this. And that gives it 2, 4, 6, 8. So in general, if we want to think about it, the lone pairs, if you add up the lone pairs plus the number of bonds that are present, for everything but hydrogen, we would get the number 4. And what that's saying is we have 4 pairs, which would equal 8 electrons, which is the goal when we're following the octet rule. So on this slide, while it just covers a few of the elements, it gives us an idea that, for example, all of the halogens. So let's take bromine. Bromine, we would predict, because it has 7 valence electrons, would have 1 bond and 3 lone pairs. Right? Sulfur is under oxygen. Sulfur also has 6 lone pairs. So it would have 2 bonds and 2 lone pairs. That's our initial prediction. So on this slide, you do need to be able to, if I say, for example, how many bonds and lone pairs would you expect carbon to have? You need to be able to say that I would expect, or it would be expected, that carbon would have 4 bonds and 0 lone pairs. Or if the question was, how many bonds and lone pairs do you expect from an element with 6 valence electrons? That would be like oxygen. Then you would say, I expect if you have 6 valence electrons for it to have 2 bonds and 2 lone pairs. So you need to be able to predict, using the octet rule, your expectation of what an element would do in terms of how many bonds and how many lone pairs. So I also now, this is something that I want to go over in terms of the language and what each is saying. So we have molecular formulas, which is what we're going to be given. And then we have something called a Lewis structure. So before we start to work on these drawing Lewis structures, I want to go over what each of these means and what they would look like. So a molecular formula would be, here's an example. Molecular formula shows us what type of atoms and how many there are of each. So molecular formulas do not have to show us how they're connected to each other, so what kind of bonds or lone pairs. It really is just telling us what's there. Okay, so a molecular formula tells us what's there, and when we draw Lewis structures, it's going to start by them giving us a molecular formula. So they're going to tell us what's there. A Lewis structure, on the other hand, shows how the atoms are bonded to each other. So it shows us what type of bonds, who's bonded to who, where the lone pairs are. And so that helps us understand bonding. But then Lewis structures, we will discover, also help us with the shape of molecules and with their polarity, which are two other things that we'll talk about. So it's not just about how they're bonded. It helps us with other things. Now you'll notice in the words it talks about single, double, and triple bonds. So single bonds are here. So a single bond is represented by just one line like that, which equals 2 dots. Oops, sorry. Doesn't like to draw dots. And equals, so that is 2 electrons being shared. Then we could also have a double bond, which is written like this. And so a double bond would be drawn as 2 lines. That equals then 4 electrons. That's why I don't like drawing all the dots, because it would have 2 shared pairs, so you'd have 4 dots. And so a double bond equals 4 electrons, because each line is representing 1 shared pair. Then we can also have a triple bond, which is not represented in this Lewis structure, but you can imagine it would have 3 lines. And then that would be 6 electrons shared. So it'd be 3 pairs of dots, 6 electrons. And so that equals a total of 6 electrons. And then, so you can have all of those single, double, triple. Also, these dots here, remember, these are the lone pairs or non-bonding electrons. So they can still have those. Now, I want you to notice with carbon, remember we predicted on the previous slide, I'm going to go back, that carbon would have 4 bonds and 0 lone pairs. So if we look here, the 4 bonds doesn't have to come as all single. Like here we have 1, 2, and then a double bond would be 3, 4. So when they talk about how many bonds, it can come in as a single bond, double bond, or triple bond. So for example, nitrogen has 3 bonds. If we look back here, nitrogen likes 3 bonds and 1 lone pair. Well, 3 bonds, that could be a triple bond. That would be 3 bonds. It could be 1 double bond and 1 single bond. That would be 3 bonds. Or it could be 3 singles. So when they talk about how many bonds, just remember it doesn't all have to be single. It could be a combination of triple, double, or single up to that particular number. All right, so that will be, we're going to stop here for that. The next thing that would come after this is learning how to draw Lewis structures. So that's going to be in the next series.